Welcome back to Re07 channel. Today, we are going to combine hydropower engineering theory with Python programming to design a small hydroelectric system. By the end of this lesson, you will know how to calculate net head, how to compute power output, and how to estimate Penstock pipe diameter, and how to select the correct turbine type. Let's begin.
In hydropower engineering, everything starts with the head, the vertical distance from the water surface to the turbine inlet. We define gross head, the vertical distance from the water surface to the turbine inlet. Head loss, energy lost due to pipe friction and bends. Net head is the real usable head at the turbine. And net head is simply net head equals gross head minus head loss. This net head is the H in the famous hydropower equation. In hydropower, the formula for power, P, in watts, is P equals eta times rho times G times Q times H, where P equals power output, watts, W, eta equals turbine generator efficiency, typically 0.80 to 0.95, rho equals water density, approximately 1,000 kilograms per meter cubed for fresh water, G equals acceleration due to gravity, 9.81 meters per second squared, Q equals flow rate of water, meters cubed per second, and H equals effective head or height difference, meters, net head. Now, instead of calculating everything manually, we will let Python do the engineering work for us. Our program will ask for 3 real-world inputs: gross head in meters, head loss in meters, and flow rate in cubic meters per second. Then, Python will calculate net head, power output in kilowatts, required pipe diameter, and the recommended turbine type. Next, we will construct a precise AI prompt to generate a Python program for automated hydropower calculation and design. Now, we will paste this prompt into the AI to generate the Python code for our hydropower calculations. Here's the full Python code that powers our Hydropower Design Tool. Next, we'll go through the Python code step by step and understand how each part works. Line 1. Importing the math library. Before doing any engineering calculations, we import Python's math library. This gives us access to important mathematical functions like math.sqrt, used later to calculate pipe diameter, math.pi, the value of pi, 3.14159, etc. Even though we don't use it in this section yet, we load it now so it's ready for later calculations. Line 2. Program title. This line simply prints a title on the screen. It tells the user that they are running the RE07 Hydropower and Turbine Design Tool. This is good practice. Professional engineering programs always display a clear header. Line 3. Asking for gross head. Here's what happens step by step. Input displays a message asking the user to enter a value. The user types a number, for example, 50. Float converts the typed text into a decimal number. The value is stored in a variable called gross head. Gross head means the height difference from the water reservoir to the turbine inlet. Line 4. Asking for head loss. This line works exactly the same way as the previous one. The user enters the head loss, which represents energy lost due to friction in the pipe. The value is stored in the variable head loss. Line 5. Asking for flow rate. Here, the user enters the flow rate, how much water flows per second. This value is stored in the variable flow rate.
Section titled Constants and Settings. This line is a comment. Python ignores it, but it helps humans understand that the next lines define fixed engineering values used in the calculations. Professional engineers always organize code this way for clarity. 1. System efficiency. This sets the efficiency, eta, of the hydropower system to 85%. In real turbines and generators, some energy is lost as heat and friction. We never get 100% conversion, so 85% is a realistic and commonly used engineering value. 2. Water density. This sets the density of water, ρ, to 1,000 kilograms per meter cubed. Fresh water at normal conditions always has approximately this density. This value is standard in all hydropower calculations worldwide. 3. Gravity. This sets the acceleration due to gravity, g, to 9.81 meters per second squared. Gravity is the force that gives falling water its energy, so it is essential in the power equation. 4. Target pipe velocity. This defines the design velocity of water inside the penstock pipe. Why 2.5 meters per second? Too fast, high friction loss and pipe damage. Too slow, the pipe becomes too large and expensive. 2 to 3 meters per second is the industry standard range, so 2.5 meters per second is a safe design choice. Calculation section. Another comment to tell us that the real engineering calculations start here. 5. Net head calculation. This calculates the net head, the actual usable water height at the turbine. Formula: net head equals gross head minus head loss. This value represents how much energy the water really has after pipe losses. 7. Pipe area calculation. This calculates the cross-sectional area of the penstock pipe. This ensures the pipe carries water at the safe design velocity we chose earlier.
8. Pipe diameter calculation. Finally, Python calculates the pipe diameter. Math.square root gives the square root. Math.pi gives the value of pi. This produces the correct internal pipe size for construction.
Explaining the turbine selection and output section. Part 1. Turbine Selection Logic. This section teaches Python to think like a hydropower engineer. In real hydropower design, the type of turbine depends mainly on the net head. High head condition. If the net head is 70 meters or higher, the site is classified as a high head project. High head sites use Pelton turbines and turbo turbines. These turbines work best with high-pressure, fast-moving water jets. Medium head condition. If the net head is between 10 meters and 70 meters, the site is a medium head project. Medium head sites typically use Francis turbines. These are the most common turbines in the world. Low head condition. If the net head is below 10 meters, the site is a low head project. Low head sites use Kaplan turbines and propeller turbines. These are designed for slow-moving, high-volume water. Why this logic is important. Instead of a student memorizing turbine tables, Python now automatically recommends the correct turbine type. This is exactly how preliminary hydropower design software works in real engineering firms. Part 2. Output section. Printing a clean results header. These lines print a neat title and separator lines. This makes the output look like a professional engineering report. Printing net head. F means formatted string. F net head : .2f means show the value with 2 decimal places. So if net head equals 45, it prints 45. Printing power output. This prints the power in kilowatts, also with 2 decimal places. Printing pipe diameter. This line prints diameter in meters, 3 decimal places, diameter in millimeters, 1 decimal place. Printing turbine recommendation. Final friendly messages. These lines give a professional closing message, just like real engineering software. Our design is now complete. Thanks for watching. If you enjoyed this lesson, please subscribe and share your thoughts in the comments. See you in the next episode.